There's a big divide on how developing systems controlled by PLCs is thought of.
Nowadays, industrial controls applications are looking more and more like software, but software development is very different from traditional PLC programming.
We're going to walk you through the difference between two approaches across a product's lifecycle. I'm going to demonstrate a traditional PLC programming approach.
And I'm going to demonstrate a modern software development approach. Let's get started. The planning phase is where everything gets kicked off. Each department gets their marching orders, and the systems integrator and the OEM start to coordinate on what the software is going to look like.
I'm promising to deliver a complete machine. All my work is contracted against a fixed bid. I can't pretend to know every future contingency, so I protect myself by padding the estimate. The OEM might pay more than they should, but at least I won't have to justify an overage later.
We perform work in 6-week sprints, and at the end of the sprint, we promise to deliver some version of the feature that we described at the start of the sprint. Development and testing is when the developer acts on a control specification provided by the OEM and produces some type of software that reflects the requirements specified in that scope.
I'm working on this by myself. This makes it very difficult to bring in additional resources that could be effective. The work gets done whenever I finish it. There's no cost-effective way to accelerate the timeline. Because I don't have access to the machine, I'm building elaborate test fixtures and small-scale hardware setups to test my logic.
We leverage the power of modern version control tools like Git in order to split a project up into multiple independent modules. This way, if we have a tight timeline and extra resources, we can simply create 2 parallel branches and work on them simultaneously, thus dramatically accelerating our timeline. All of our code is peer-reviewed, and each of us adheres to a strict set of coding guidelines so that it's easy to understand what other people have written. We have access to powerful simulation tools. These are high-fidelity representations of what the code will actually do when it's on the machine. At the start of the commissioning phase, the machine has been fully assembled. Electrically, mechanically, it's ready to go. The developer is now on site at the OEM facility where the machine resides for the first time and is preparing to load the software onto this system.
I can only do my testing after all the mechanical and electrical work is complete. I have to be on site to do it since debugging the code involves coordinating with operations and maintenance technicians. Sometimes the stage takes weeks or even months. I'm working 12 to 18 hours a day and I'm prone to burnout.
Thanks to our simulation tools, we've already validated that the bulk of our logic is working. We know that the process control is working properly. And what remains to be tested while we're on site with the machine are physical things like I/O or protocols or communication with other systems. When there are issues that arise during commissioning, it's very easy to perform a root cause analysis because we know that the bulk of our code base is functional and this smaller portion is the only spot where problems could arise. Once the system integrator and the OEM finish their work on the machine, it's time to complete the order cycle by shipping it to the end user. Of course, this customer expects the machine to be ready to run right out of the gate and to start to produce on day one.
Unfortunately, because of development bottlenecks, budget constraints, and the fact that we couldn't easily adapt to the unforeseen challenges during the development process, the machine is being shipped to the end user's site half-baked. The OEM will have to send the developer of the system to the end user's site to continue debugging.
Our machine was shipped complete, thanks to thorough testing and tight collaboration between all stakeholders up until this point in the project. The end user is therefore very satisfied with the performance of the system and doesn't have to worry about dedicating technical resources to learning the code base or being able to make ad hoc changes to it. The system is performing as specified. Once the machine is running production at the end user facility, we're now entering into the last phase of the project lifecycle that we'll call ongoing support.
To understand an issue or fix a bug, I have to connect to the physical machine. I typically have to travel to the machine's location at the end user's facility. Once on site, I'll discover that local resources have made modifications to the software, with no modern version control to track what they've done. Identifying the changes becomes an inefficient process. This leads to increased downtime on the machine and increased on-site time for the developer.
We leverage best practices from the continuous integration and continuous delivery paradigm in order to automatically build, test, validate, and deliver our software to a fleet of machines across the entire world. Best of all, our automated content and software delivery pipeline is reliable and highly scalable. So each of us is freed up to really focus on the creative, interesting work that we were hired for in the first place.
Modern software practices offer very powerful and proven solutions.
And at Loop, we leverage these amazing tools to revolutionize the entire life cycle of industrial controls applications.
Come see our process in action at loop.team.